Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, we're going to focus on solving medium-sized systems of linear equations. And what I mean by medium-sized systems is that we're going to focus on solving systems of three linear equations with three unknowns. And that's what actually part A is going to focus on, is an algebraic method for solving 3 by 3 systems. Of course, we're going to introduce what a 3 by 3 system actually looks like also in part A. And in part B, we'll focus in on applications. But this is the lecture for part A here. By the way, there are systems that are much larger than 3 by 3 systems. In fact, most systems that occur for applications in the real world are on the order of maybe hundreds to thousands of equations and unknowns. So these are kind of an introduction to how methods can be built to solve other systems, larger systems, quickly. The first thing I want you to recall is that a system of equations can graph out pretty nicely as at least a 2 by 2 system, or system of two equations, two unknowns, could graph out nicely on a two-dimensional Cartesian coordinate plane. And the reason why it graphs nicely if you have two equations and two unknowns, let's say y equals 3x plus 1 and y equals a negative 2x plus 2. If we wanted to graph this system of equations, recall that, well, you'd graph both. So here's one of them. I'm just going to pretend as though that's y equals 3x plus 1 here. And the negative 2x plus 2 would be something like that. Okay. The fact that we can graph this on an xy coordinate system is because we only have those two variables, an x and a y. But in this section, or this lecture, we're going to focus on graphing things, or not graphing, but solving systems where we have three unknowns. So we will be focusing on solving things like 3x plus 2y plus z is equal to 10, and then we'll have another equation. Since we have three unknowns here, we'll need two other equations actually, like negative 2y plus 8z is equal to 13, and let's say 3x minus 4z is equal to 1. That's a system of three equations and three unknowns. Now, because we have three unknowns, we need an axis for each of them. And so normally we would draw on a coordinate plane, we draw an x and a y axis, and here's where you have to use some imagination. Pretend for a moment that this is the x-axis and this is the y-axis, and it's lying flat on the ground. Kind of hard to tell right here, and you have another axis that we'll call the z-axis coming up. Okay. So this is the positive x direction, the positive y direction, and the positive z direction. And when we want to graph any of these equations, they'll end up not being lines, but in three dimensions. The three-dimensional equivalent of a line is a plane. The best way to understand this is to just look at a computer-generated three-dimensional graph. So where I'm at right now is I went to Wolfram demonstrations. I just Googled Wolfram demonstrations. And then I typed in this title, Planes, Solutions, and Gaussian Elimination of a 3 by 3 Linear System. Essentially, it's just giving me an example of what three equations and three unknowns looks like. Each equation, it develops basically an infinitely large sheet of paper. And you can see in this example, one equation is represented by this blue sheet of paper. One equation is represented by this yellow sheet of paper, and one equation is represented by this green sheet of paper. And just like in a system of equations for two unknowns and two equations, you have a single point of intersection, and that single point of intersection is called the solution. But the thing with 3 by 3 systems is that there's a lot more ways that you can end up with infinite solutions. Before we take a look at those, I adjusted the equation slightly here so that you see here's our three equations. And you could actually see the equations down here. That's negative 5z, negative 7y, and 9x. They're all equal to 0. And so it ends up giving me three perpendicular or normal planes. And the intersection, the common intersection, is a single point, the center. But now if I move to a more advanced example where I have negative 3z is equal to 0, that's our first equation, 7x minus 4z is equal to 0, and then 7x equals 0, you can see that I have three sheets of paper, but they all are cross on the same plane here. Very hard to see, but that red line there is where all their solutions meet up, or where all the planes meet up. So there's an infinite number of solutions. They all exist on this line. Remember, the solution to a system is where your lines or your planes cross and where they share common points. And these three pieces of paper all share an infinite number of common points. I recommend that you go to this website and search for that. Again, it's just Google Wolfram demonstration, and then it's a free download to download this player. Here's yet another example. This is actually a graph of three equations and three unknowns, but they're all the same equation. So in other words, they're all the same sheet of paper. So you have three sheets of paper that are lined directly on top of each other. So this is another example of a dependent system where there's an infinite number of solutions. And finally, you have the type of system, just like with 2x2 systems, in other words, systems with two equations and two unknowns, there is a possibility where you have no solutions. Same thing with 3x3 systems. It's hard to see here when I'm at this angle, but when I start tilting it, you could see that these three sheets of paper do not meet at a common point. I mean, one sheet of paper meets another, but they're not all three sharing a common point of intersection. So this actually has no solution at all. This is a very interesting style of system. And like I said, with 3x3 systems, this is very, very common that you end up with no solution. It can happen much easier than it can with a 2x2 system. So now that we spent some time kind of going over the visuals, it would be very difficult if your instructor asked you to graph these by hand. So you can kind of see why in those previous examples. But now that we've kind of gone through those, let's go ahead and delve into solving a system of three equations with three unknowns. There happens to be 1, 2, 3 equations here. I'll call them row 1, row 2, and row 3. And we wanted to solve these. Now, I have this set up in a very special format that is officially called triangular format, but this is set up very nicely to where we can actually back solve this system. So let's go ahead and see what I mean by back solve. When you're back solving a system like this, you just basically pick the equation that's easiest to work with. And it looks like this last equation is easiest to work with. So if you divide both sides of that by 3, so that means take 1/3 and multiply it by row 3, it'll become the new row 3. Remember, my notation in the previous lecture was like this, where I basically this is my fast way of noting what's happening to an equation. When you do that, well, 1/3, or in other words, dividing this equation by 3 down there, it gives you a single z is equal to 1. Everything else has remained untouched, so I'll go ahead and write that up here like this. 3x plus 2y plus z is equal to 6. Well, now that I know what z is just 1, I can plug that into the previous equation. So in other words, row 2, I could plug in z equals 1, so I get 2y plus 1 is equal to 3. Or in other words, 2y is equal to 2. Or in other words, y is equal to 1. So let's see, I'm going to write my letters over here so I have them nice and organized. We found out that z was 1 and y was 1. So now that I know what z and y are, I can then go to row 1 and plug in those values for z and y. 2 times 1 plus 1 is equal to 6. That's 3, subtract 3 from both sides. That implies that 3x is equal to 3, which implies that x also is equal to 1. There we go. So you see that we can easily find a solution to a system if it's given to us in this very special form. But to be very honest with you, if somebody handed me a system like this, I would consider myself lucky. And you should as well, because you could solve this whole system by going to the easiest equation to solve first, and then finding out what z is, and plugging that into the next equation up, and so on and so forth. That's the strength of this format. But in reality, rarely are you given the luxury of having an equation set up like this. By the way, your answer would be written as x equals 1, y equals 1, z equals 1, or as an ordered triple, in other words, as a point, 1, 1, 1. Just like you would have a point x, y, this is a point x, y, z. Now let's try our hand at a different example. This one is not as trivial. In fact, this one's pretty tough. So let's go ahead and talk about this. This is row 1, row 2, and row 3 again. And before you go tackling a system of equations that looks like this, remember what we said about systems of equations, that you can multiply a row by any number that's not 0, and the solution will still remain the same. So in other words, I could take that row 2 and I can multiply it by 2 if I wanted to, and let that become the new row 2. You could also take that row 3 and multiply it by the number 3 to make that the new row 3. The reason why I'm choosing to do this, obviously, is to take care of those fractions that occur in both of those lines. So row 1 I haven't done anything with. I'll just leave this as x plus y minus z is equal to 2. Twice row 2, let's see, 2 times 1/2 x is a regular old x. 2 times a negative y is a negative 2y. 2 times a 1/2 z is a positive regular old z. And remember, you multiply the right hand side by 2 as well. So 2 times a negative 1/2 is a negative 1. The third row I'm also going to multiply by 3, so we get 3x and then a single y minus 2z, and finally equals 4. Remember, you are multiplying each of the objects in that row by the number 3. Okay, so now we have this nice system that no longer has any fractions in it. So at this point, my recommendation is to think about what your skill set is. All you know how to do right now is solve systems that are 2 equations with 2 unknowns. So let me write that down. And notice I wrote 2 by 2 systems. That means 2 equations with 2 unknowns. Well, this has 1 too many equations and 1 too many unknowns. So if that's the case, you could choose to kill off a variable using the elimination method. So pick a variable you'd like to kill off, choose wisely. The x's here would be very easy to kill off. The y's are actually extremely easy to kill off, and so are the z's. They're all very easy to kill off in this system. So I'm just going to choose arbitrarily to kill off the y's. Okay. Now pause this video, you try killing off the y's, and then when you come back, see if you have the same result as I have. What I'm going to do to kill off the y's is I'm going to take twice that row 1 so that I can make the coefficient on this y a positive 2. And I'm going to add that, actually I'll write the addition this way, I'm going to add that to row 2. So here we go, let me go ahead and write that out here. Twice row 1 would be 2x plus 2y minus 2z, and don't forget the right hand side, 4. Row 2 I'm just going to copy, x minus 2y plus z is equal to a negative 1. Now that I have this, I'm going to go ahead and add these up, right? Because that's what I said, I'm going to take twice row 1 and add that to row 2. The reason why is because, again, 2 of these y's plus a negative 2 of the y's, they'll cancel. So it basically kills off a variable for me. When I add these up, I get 3x, what is that, minus z is equal to 3. Now, I'm going to choose a different set or combination of equations here so that I kill off the y's again. So this time, I'm going to take row 2 and I'm going to add it to twice row 3. If I do that, look at twice row 3, I'll have 2y here, I'll be adding a negative 2y to that, so the y's will cancel there as well. The reason why I do this, so let me copy this while I talk. The reason why I do this is so that we end up with two equations, the equation that we just found over here on the left and the equation we're about to write down on the right, that only involve x and z. So then we're basically back to what we learned previously, two equations with two unknowns. All right, twice row 3 is just going to be a 6x plus 2y minus 4z is equal to, and again, twice that 4 is 8. So I'm going to add these up. I get 7x, what is that, minus 3z is equal to 7. So now I have these two equations. After killing off y, I have 7x minus 3z is equal to 7, and I have 3x minus z is equal to 3. So I'll group those two up into a nice little system. 3x minus z is equal to 3, and 7x minus 3z is equal to 7. And I'll group those up nicely. And now I can easily kill off a variable. In fact, I'm going to try to kill off z here. I'm going to call this row 1 and row 2. I know that I have row 1, 2, and 3 labeled up here, but now I'm just going to be working with this system, so I'm just going to call that row 1 and row 2. And what I'll do is I'll multiply row 1 by a negative 3, and I'm going to add that to row 2. The reason why I'm choosing negative 3 is because I want to kill off the z's here to find out what x is. So negative 3 times a negative 1 is a positive 3. So this will be a positive 3z's plus a negative 3z's. They disappear. Okay. So here we go. This gives me a negative 9x plus 3z is equal to negative 9. Remember, you're multiplying everything by that negative 3. And in row 2, I'm just going to rewrite 7x minus 3z is equal to 7. Add these up. And when you do that, negative 9x plus 7x is a negative 2x. The z's cancel by design. And this will be a negative 2 here, which means that x is equal to 1. Now to keep it clean, I'm going to go ahead and write my result up here. X is equal to 1. Well, now that I know what x is, I'll substitute it back into one of these equations over here. It doesn't really matter which one. In fact, I'll probably plug it into row 1 here. So, so let me just indicate that. I'll go ahead and rope it around there. So I get 3 times 1 minus z is equal to 3. Well, I'll subtract 3 from both sides to get a negative z is equal to 0, or in other words, z is equal to 0. Cleanliness, write this here. So now I know what x is, I know what z is, so now it's my time to find out what y is, and to do that I can actually go and find out what y is by plugging x and z into any of the original equations, either any of these three right here or any of these three right here, but whatever you choose, choose an equation that's easy. This top one right here looks like the easiest equation ever. So I'm just going to plug it into that equation. So here I go. X was 1 plus, we don't know y, minus z is 0 is supposed to be 2. Subtract 1 from both sides, I get y is equal to 1. I'll circle that up and write it up top. You can always check your answer by plugging those into the original equation or the second set of equations. However, I know that's right, so I'm not going to bother plugging it in. So let me write down the method. And I'm not one for methods, but really when you're starting to solve 3x3 systems and 4x4 systems and so on and so forth, it is pretty important to know kind of a systematic way to do it. The systematic way is really to clear fractions. That's the first thing we did in that last example. If you have fractions, kill them off. Same thing with decimals. If you have decimals, multiply both sides of those equations by 100 or whatever you need to get rid of decimals. Choose a variable to kill off because you have 3 variables. That's really one too many. So choose a variable to kill off. Make sure it's an easy variable. And the way you're going to kill that variable is you're going to basically choose a couple rows, like row 1 and 2, or row 1 and 3, or row 2 and 3. And you're going to use elimination to kill off the variable, not once, but twice, because you're going to need 2 equations. So that would be, let me just hop back to my previous example. That would be this step right here where I chose rows 1 and 2 and then rows 2 and 3 to kill off y. And when I did that, I ended up with 2 equations involving only x and z. And that's what this says right here, to get a 2x2 system. Now, solving the 2x2 system is old hat. We should be pretty good with that. So solve that resulting 2x2 system, and then once you get that solution for that 2x2 system, which means you have x and z, the values for that, or whatever variables you're using, then you can find the last remaining variable by plugging those values into any of the earlier equations. Now, I'm going to continue forward here, and I want to present an example that can be a little challenging for students because they tend to run in circles. If you don't have a system set up properly to begin with, you will run in circles when you try to solve a system. You'll not know how to plug x into something or y into something. You'll think, oh, I know what x is, so let me replace these x's with y plus z, which is absolutely fine, but it doesn't really mesh well with kind of how I teach. So instead, I'm always known as teaching kind of a lengthy method to do things. So I'm going to teach you a lengthy method to do this. I'm going to move all variable terms to the left-hand side. So I have x minus y minus z is equal to 0. I have a negative 2x plus y plus z is equal to 0. Again, I'm just moving everything to the left-hand sides. A negative 3x plus y plus z is equal to 0. Okay. And now I'm going to choose a variable to kill off. And there's quite a few choices here actually, but I think I'll kill off the z's. Why not? So let's, in fact, I'll make that declaration, kill off z. So I'm just following my instructions earlier. I don't have really any fractions to clear, so I'm just going to kill off the variable z. And let me choose a finer chisel for my pen here. So what I'm going to do is take row 1 and I'll add it to row 2 because that actually looks to be a very easy kill right there. So x minus y, not plus, but minus z is equal to 0. And negative 2x plus y plus z is equal to 0. When I add those two up, I will get the following. The z's cancel. Actually, the y's cancel. Very rare that that happens, but it sometimes will. And you get negative x is equal to 0. Or in other words, x is equal to 0. Awesome. But what I'm going to do now, if you end up getting something like this, where you get like, oh, all of a sudden when I decide to kill off a variable, my x, I find out that x is actually 0, then what I recommend is rewriting your system with that value of x plugged in. So in other words, where I see these x's, I'll replace them with zeros. Okay? And in that case, I get this. Negative y minus z is equal to 0. A y plus z is equal to 0. And a y plus z is equal to 0. Now you could choose anything you want, really. You could choose to kill off any which two equations. But you see these last two are the same equation. So I'm not going to bother rewriting it. I'm just going to add row 1 to row 2. It does happen every once in a while that you get two equations in your system that are exactly the same. That signifies something very special, but we're about to see it anyway. So we get negative y minus z is equal to 0. I'm just going to kill off y here. And y plus z is equal to 0. But look what happens when I add these two together. I get 0 on the left-hand side because all the variables cancel, and 0 on the right-hand side, which is always true. And remember what we said about a system where you get to a constant is equal to itself. That means that this system must be a dependent system. And in fact, dependent, since it has solutions, we call it inconsistent, or not inconsistent, we call it consistent because it has a solution. But because there's an infinite number of them, we call it dependent. So consistent and dependent system. This will happen just like it did when we solved 2x2 systems. So when you're solving systems and you get down to where you get something like 0 equals 0, you know you have a consistent and dependent system. In other words, that you have an infinite number of solutions. So let's go ahead and try another example here. And what I'm going to do, actually I miswrote slightly there. I'm going to go ahead and multiply row 1 by the number 2, make that my new row 1, just so that I can get rid of fractions. And I'm also going to multiply row 3 by 3, so that I can get rid of that silly fraction there as well. It'll become my new row 3. Remember, you're allowed to do stuff like that. So row 1 is going to become x plus 2y is equal to z. Row 2 is still the same old row 2, so it's x minus y is equal to a negative 2 minus z. And finally, row 3, when I multiply everything by 3, I get a negative 3x. Let's see, negative 6y is equal to a negative 3z plus 4. Now I got to clean this up. I want all my variable terms on the left-hand side. Just still kind of keeping with my nice setup, so I'll do that. The first equation is just x plus 2y minus z is equal to 0. Second equation is x minus y plus z is equal to a negative 2. And then finally I have a negative 3x minus 6y plus 3z is equal to 4. Now I have decisions to make, right? I have to figure out which variable to kill off. I think I'm actually going to, again, kill off the variable z here. It looks like it'd be a nice, fun variable to kill off, so we'll do that, kill off z. The way I'm going to do this is I'll take first row 1 and add it to row 2. That'll kill off a z. So we have x plus 2y minus z is equal to 0. And we'll also have an x minus y plus z is equal to a negative 2. So when I add these two together, I'll get 2 of those x's. I'll have a single y. The z's will cancel appropriately, and I'll have a negative 2. So there's an equation. And now I'm going to go ahead and kill off z again using a different combination of those equations. And in fact, I'll choose 3 times row 1 and add that to row 3. The reason why is because if I multiply row 1 by 3, this will become a negative 3 of those z's. When I add that to 3 of them, all the z's cancel. Here we go. 3 times row 1 becomes 3x plus 6y minus 3z is equal to 0. You wouldn't believe how many people like to write that as 3 over there, by the way. 3 times 0 is 0. And then finally, negative 3x minus 6y plus 3z is equal to, let's see, 4. I'm not really multiplying this by anything. And when you add these up, something strange happens. The x variables cancel, the y variables cancel, and the z variables cancel. So the left-hand side is 0, but the right-hand side is 4. And that is never true. And like we've said in a previous lecture, if you are solving a system and you get something like 0 is equal to 4 or -1 is equal to 8 or something like that, something that's never true, there's never a solution. So there's no solutions, which means that you have an inconsistent system. And this is the kind of system that I had shown just a moment ago, or a few moments ago. This one right here, where you have a bunch of planes, these sheets of paper, that never meet up. They don't have a common meeting point, so there's no solution. Now at this point, what I'm going to do is stop this video and then I'll put up a part B. And in part B, it's going to focus on solving applications that require systems of linear equations. So that's kind of the one that a lot of students really should watch.